We're going to begin our study of acids and bases today. So the first thing that really you need to work on is naming acids and bases, because I will expect you to be able to do that. So if you need to go back and watch one of the earlier videos on acids and bases, now would be a good time to do that, and then you can come back and do this after you've done the naming piece. All right, so there are a couple definitions of acids and bases, and we're gonna talk about two of them, and the third one we're just going to kind of pretend doesn't exist. All right. So one of the definitions is arrhenius. Okay, and arrhenius acids increase the concentration of hydrogen ion or H3O plus, which is called hydronium ion, in solution. Okay, so let's do an example here. So here's hydrochloric acid. All right, and I could write what happens with hydrochloric acid as a dissociation reaction. So here's my hydrochloric acid. It's dissociating in water to form H plus Cl minus. All right, so here's my standard dissociation reaction. Now the problem with this is this proton, this H plus, by the way, H plus is equivalent to a proton, right? Because hydrogen atom has one electron, one proton, and 0 neutrons for the most common isotope. Okay, so if you remove the electron to make H plus, what you have left is just one proton. So you'll see the term proton used interchangeably with hydrogen ion. Okay, so this proton does not actually just kind of float around by itself in solution. What happens is it'll be attracted to the partial negative charge of water. Remember, water has a dipole, so it's got a partial negative charge. So one of these protons will end up just attaching itself to a water. And I can represent that in a different way. HCl plus water. Okay, so now this is the water that's going to be my kind of carrier, yields H3O plus Cl minus. All right, now this is our preferred method in this unit of writing what's going on in this reaction. Okay, so there's some HCl giving up its proton, but this time it's giving up its proton to water, which accepts the proton to become H3O plus and Cl minus. All right, now notice that my charges are always balanced. So net charge on the reactant side is 0, net charge on the product side is 0. That's very important when you're making these reactions. You can't have like weird charges happening all over the place. Okay, so if our arrhenius acid increases concentration of H plus or H3O plus in solution, an arrhenius base increases concentration of OH minus. Okay, this is also known as hydroxide ion. Okay, and you'll see this rather a lot. Hydroxide ion is very important. So hydronium and hydroxide, very important to know. Okay, now most bases fall into one of these two categories. Okay, either a metal hydroxide or an amine base. So amine just means nitrogen containing. So a nitrogen containing base. Those are the two very common types of bases that you'll see lots and lots and lots of. Okay, now for the metal hydroxides, we are always just going to write them as dissociation reactions. And I'll show you why in a moment. Okay, but you just have to remember that these metal hydroxides you always just treat as a dissociation reaction rather than the preferred, what we're going to call a proton transfer reaction. Okay? So here's my dissociation reaction. Notice that by dissolving the solid in water, I make sodium ions and hydroxide ions. So importantly, I make hydroxide ions, so this would fit the bill for an Arrhenius base. Now, ammonia also works, okay? NH3 plus H2O. Now, these ammonia bases are great because you can write them with the water in this preferred method, and we're going to talk more about this preferred method later, okay? Forms NH4 plus OH minus, and there again is my OH minus, so this also fits in the definition of an Arrhenius base. Now, I just want to show you real quick as kind of an aside why we don't write this sodium hydroxide reacting with water. Okay, so sodium hydroxide reacting with water, and I'm going to write water as HOH because that's how it reacts. Okay, now if I look at this, if you look at this, you should see immediately that this is a double displacement reaction. Okay, so one of my products is going to be HOH, being water. Now notice that my water just gets regenerated on both sides. That's why we don't do it. Okay, and these, okay, these ions, the sodium ion and this hydroxide ion, actually break apart because we're in water. All right, so see how this equation and this chemical equation and this chemical equation are really saying the same thing, okay? This one's just a little bit cleaner. So that's why we choose to represent metal hydroxides as just a dissociation, whereas all other things we're going to say are reacting with water, okay? So you need to get used to that reacting with water to form something, okay? All right. Now the next thing that we want to talk about is strong acids and strong bases. So a strong acid is one that ionizes completely in aqueous solution. Okay? So if we go back and we look at HCl, okay, HCl forms these ions. By the way, so this is a dissociation reaction, and this is an ionization reaction. Okay? Notice that they perform the same role, but it'd be hard to really say that this is really a dissociation reaction because what's really happening is the H plus is going on to something else. Okay? So HCl is an example of a strong acid. This is not really at equilibrium. Okay? It's not really at equilibrium. This reverse process doesn't really happen. What happens is we kind of dissociate completely in aqueous solutions. Okay? So that means that strong acids would also be strong electrolytes. So all the things that were true of strong electrolytes are also true of acids. Okay? So here are some examples. HClO4, HCl, HNO3, so perchloric acid, hydrochloric acid, and nitric acid are all examples of strong acids. Okay? A weak acid releases few hydrogen ions in aqueous solutions. So hydronium ions, anions, and dissolved acid molecules in aqueous solutions. So example, HCN. Okay? So when HCN reacts with water, okay, I'm going to transfer the proton over because I'm saying that this is acting as an acid to make H3O plus H3, how did I do this? H3O plus the anion CN minus. Okay, so what happens is when you put HCN into water, you establish this equilibrium, but weak acids favor the reactants, which means that I'm going to end up with some of this just unionized cyanic acid just dissolved in water. Okay, so that's what we got. Okay, organic acids. So anytime that you see COOH, are also weak acids. And so the kind of example that the book uses a lot is acetic acid. So that's C2H3O2, HC2H3O2, or HCH3COO, can be written either way, and I will write it both ways often so that you're kind of comfortable with both. Okay, so these are also examples of weak acids. Okay, and again, just like a strong acid, there are also strong and weak bases, and the strength of a base depends on the extent which the base dissociates. Strong bases are also strong electrolytes, no surprises there. And I have now instructed myself to look at the acid strength table with you. So here we have the acid strength table. You can see increasing acid strength table. So these ones up here, HI, HClO4, HBr, HCl, H2SO4, HClO3, HNO3, these are all really strong acids. Okay, and the bases go kind of the opposite direction. And just in case you're unclear on things, I have a list of the strong acids down here and the strong bases down here. Notice that the strong bases are all metal hydroxides. That's kind of important to keep in mind. Okay? So that's acid strength. The next thing that I want to talk about is another definition of acids and bases. And this one's Bronsted-Lowry. Okay? So Bronsted-Lowry acid is a molecule or ion that is a proton donor. So HCl acts as a Bronsted-Lowry acid when it reacts with ammonia. So here we have an example. Okay? Now notice we said earlier that this was an acid, HCl was an acid, and NH3 was a base. But if you look at this reaction, this doesn't fit the definition that we had for arrhenius acids and bases. So even though we know that this is an arrhenius acid and this is an arrhenius base, we're not actually making H3O plus or OH minus. So it doesn't actually fit the definition that we had before. So that's where Bronsted-Lowry came in. Okay? So now I want you to think about what's happening in this reaction. Okay? And see if you can name this type of reaction based on what we've been talking about. If you look at it really carefully, this NH3 is gaining a proton, making it NH4+, which means that this HCl is donating a proton, and this NH3 is accepting a proton. This is a proton exchange reaction, or proton donation reaction, or yeah. Now, interestingly, water can act as a Bronsted-Lowry base. So here's water, and it's donating a proton to NH4+. Okay, so this is our proton donor. Here's our proton acceptor, and that makes this an acid. Okay. A Bronsted-Lowry base is a molecule or ion that is a proton acceptor. So ammonia accepts a proton from hydrochloric acid. So if we go back up, in this first example, hydrogen chloride is our proton donor, which means it's our acid. NH3 is our proton acceptor, which makes it our base. Okay. Here, NH3 is also our proton acceptor, which again makes it our base. Here's just that example again. Okay? So the hydroxide ion produced in a solution by arrhenius hydroxide bases is a Bronsted-Lowry base because the OH minus can accept a proton. Okay? So that's Bronsted-Lowry stuff. All right. A monoprotic acid is an acid that can donate only one proton. all right, or 1 hydrogen ion per molecule. So examples of this, HClO4, HCl, HNO3. Notice HClO4, HCl, HNO3. They have 1 proton to donate, okay? They only have 1 ionization step. So here's HCl, it's donating, so here's our proton donor, here's our proton acceptor. So this would be our acid, and this would be our base. Okay, HCl is donating its proton to make H3O plus and Cl minus. A polyprotic acid, on the other hand, can donate more than 1 proton per molecule. So examples H2, notice the 2, H2SO4 and H3PO4. Okay, these have multiple ionization steps. So, for example, sulfuric acid would have 2 ionization steps because it can lose 2 protons. So the first ionization step is H2SO4 plus H2O yields H3O plus HSO4 minus. Notice that my net charge on the left side, on the reactant side, is 0, it's neutral, and the net charge on the product side is 0, okay? So our charge balance is fine, and everything's balanced, but I create this HSO4 minus species, okay? Species is a term that I'll use a lot in this chapter. It just means, just like a scientific way of saying thing, okay? Now this HSO4 minus, if I look at it, this proton I can also lose. So it can undergo another round of dissociation, HSO4 minus plus H2O yields H3O plus SO42 minus, okay? Notice that I could combine these. I could add this up, okay? HSO4 minus would be an intermediate, and I'd get H2SO4 liquid plus 2H2O yields 2H3O plus SO4 2 minus. So you have to kind of be aware that these polyprotic acids, you could either write out the ionization steps individually, or you could write it as an overall equation, okay? So a solution of sulfuric acid contains H3O plus, HSO4 minus, and SO4 2 minus. Now H2SO4 is one of the strong acids, right? Which means that this first step, there it is, H2SO4 to HSO4 minus, this is a strong acid. So this only happens in this direction, whereas this is at equilibrium, okay? Hence why when I make this list here, there's no H2SO4 because it dissociates completely. Okay? Now, so that's polyprotic acids. There's also diprotic acid, type of polyprotic acid, that just donates 2 protons. So an example of that would be sulfuric acid. And there's also triprotic acid, yon yields 3 protons. Okay? So all of this stuff today that we've done today will seem pretty easy, all right? But again, remember that day 1 is always fundamentals, and you want to make sure that you've got the fundamentals down before I increase the complexity. So make sure that you're comfortable with all of this stuff, especially writing those ionization reactions where an acid reacts with water to form hydronium and an anion, or a base reacts with water to form hydroxide and a cation, okay? So just make sure that you kind of keep these things in mind and that you really focus on learning the stuff that you need to learn today.